All right, let's start. So in our last lecture, we stopped at why we need to do testing. But remember, in our last lecture, we only answered the question of why we need to find bugs, why we need to have dependable software. But we didn't answer why exactly do we need to do testing, because there are many other techniques for finding software vulnerabilities or bugs. So today we are going to learn more about software quality assurance techniques. So this is today's outline. So first we will introduce two important concepts, verification and validation. And then we will learn different types of verification and validation techniques. And after that, because we are, most of you, I believe, are from software engineering, right? So we are still software engineers. And let's see how can we do verification and validation in software development. And after that, we will learn some basic principles to do program analysis and testing. So first, let me do a quick introduction of software verification and validation. So remember, in our last lecture, we have discussed we would like to build dependable software. And can you still remember what are the 4 desired properties for software dependability? If you can't, you can find it here through this link. Actually, they are correctness, reliability, safety, and robustness. And the primary process of ensuring or guaranteeing that we are building dependable software are the process of verification and validation. But these two words, they sound very similar, right? They both start with the letter V. So here are the definitions of verification and validation. So first, verification. Verification is the process of proving the system conforms to certain specifications. And validation is a process of proving that the system meets the user's requirement, meets the actual need of the users. So what's exactly the difference here? So this may sound confusing, right? So verification is to check if the system conforms to certain specifications. And what's the difference between a specification and the actual need of a user? So let's use an example to demonstrate this. So this example is actually from a tragedy. And actually, in our last lecture, we have learned that software failures could end up in many very severe consequences. And I don't know, have you heard about the case or the news of Boeing 737 MAX? You all have heard about it, right? So actually, it is now grounded. So none of the it is not used anymore. This type of flight, and there are 2 major crashes that led to this worldwide grounding. So the first one is happening in 2018, where a plane crashed in Indonesia, and the second one crashed in Africa. And the reason behind this is actually caused by the failure of a system called maneuvering characteristics augmentation system, or MCAS. So this is actually a malfunctioning of this MCAS that led to the crash. So this is a buggy system.
I actually know a thing or two about that. Wasn't malfunction because the plane crashed, but the software the whole time was intended. It's just
we will talk more about the details later.
They didn't want to train the pilots on the new planes at different aerodynamics.
Yes, yes. Actually, this system. So there are many reasons behind the failure of this system, and one of them is because the pilots are not well trained to the new system, and the other one is actually it has software issues. So, but you may have a different opinion. But let's continue first. So the software issue here is that this software was designed to activate when it detects the plane is losing speed. So if you have, because now we are in a physics building, so if you have learned some basic physics, so if the plane hides down, it is converting the gravitational potential energy into kinetic energy. So it will. If the plane hides down, it will gain speed and lose altitude. So this MCAS, once it detects the plane is losing speed, it will try to drag down the plane. And both of the crashes happens actually right after the plane has taken off, because when the plane takes off, the speed is not that, it doesn't have a very fast speed, and it doesn't have a very high altitude. But the MCAS will keep dragging down the plane, and this is actually what happened for the Indonesian crash. So we can see the blue line is the altitude of the plane. We can see that the pilot is trying to struggle to fight against this MCAS system by pulling up the plane before it actually crashes. So this software is designed to take over the control of this plane and try to make it head down. So this is the design of this software. So the software was told to bring the plane nose down if the plane loses speed. So do you think is this a problem of verification or validation? Because the software is told to drag the plane down to gain speed. So remember the definition of verification and validation. So verification is to check whether the software meets the desired specification, and validation means whether the software actually meets the need.
The question is, does it make sense? You asked if it's verification or validation, but the answer is yes.
Oh, sorry. So you can answer yes for verification, no for validation. Sorry about this. I modified. Wait, not this one. Oh, I can't modify it. But let's say yes stands for verification and no stands for validation. And let's check the results. Oh, it's actually quite even. Actually, maybe let's wait for more. The result is quite even. So actually it is the problem of validation. So, like the gentleman behind just said, it is arguably the problem of the software, because the software does what it was told to do. So it was told to bring down the nose of the plane once the speed is low enough. So the software does nothing wrong, but the specification is wrong. So there's a discrepancy between specifications and the actual need of the users, or the real world, or the desired behavior in real world. So that's why this is actually a problem of validation instead of verification. And in reality, most of the software running on a plane has been formally verified by experts. Not the entertainment software, but those flight control related software. So let's come back to the difference between verification and validation. So according to this guy called Barry, so verification is related to, are we building the product right? And validation is related to, are we building the right product? So verification is more about the process of building this software, and validation is whether this built software is functioning correctly or not. And here are more details about verification. So verification mainly concerns about, is the implementation consistent with its specification? So in the previous case, the software was doing what it was told to do, so it is verified, and it has no problem with verification. And these specifications could come from different sources. So one of them is the source code and requirement specification. And there could be other specifications, like from the design of the architecture. And there could be test oracles and requirement specifications as well. So they are related to different stages of software development. And verification is more like an experiment. So it is, an experiment is more like in a controlled environment. And it cares about, does the software works under the condition we set. So it is more like in a controlled environment. So we can perform trials, evaluate the software, and provide evidence for verification. And here are some more details about validation. So validation deals with, does the product work in real world? So does the software fulfill the user's actual requirements? So it's not the same as conforming to a specification. So a verified software could be invalid. So this is why the plane crashes. So validation shows that the software is useful. And verification shows that the software is dependable. And both are actually needed before we release the software. And here is a more detailed comparison between verification and validation, but don't get overwhelmed by the content here. So I will highlight some key points. So the first one, remember in our first lecture we have discussed what's the difference between static methods and dynamic methods. So static methods means that we don't need to execute the target system, while dynamic methods means that we need to actually run the target system. And in most cases, verifications are considered static, while validation are considered dynamic. So that's why testing belongs to validation. But there might be some discrepancies in from different sources or from different textbooks. But I think this one makes the most sense. So let's stick to this one. And Where for verification in the third row here, it mentioned that it is a human-based checking or human-based process. But actually, now we have a lot of automated or automatic verification techniques, so it doesn't have to be human-based, or it doesn't have to be done manually. So for verifications, and for validation, as we mentioned, it is mostly considered as a dynamic process. So testing, which is the major topic of this course, belongs to validation. And both of them are complementary to each other. So verification can help to expose issues that validation couldn't, while validation can help to find bugs or issues that verification cannot find. And there are several limitations for verification and validation. So the first one is complexity and cost. So it is a costly process to validate and verify these software, especially when the product is when the code is very complex. And especially for verification, if you do formal verification, you will need to invite some experts to do it manually, and that is very costly. And remember that in our last lecture, we mentioned that some big companies, they are even releasing bounties for external hackers or testers, and those bounties are very attractive. And that's only for the external members. Imagine how much do they pay for the internal testing teams. So it is actually a very costly process. And the second limitation we often encounter during verification and validation is often the incomplete coverage. So for verification, it is challenging because sometimes we don't have enough time, we don't have enough people to do the verification for every piece of code. So that's where the incompleteness of verification comes from. And for validation or for testing, it is by nature not, it is a nature that we could cover every state of a particular program. So that's why the incomplete coverage is a problem here. And the third problem is called tool limitations. So because we are not doing everything manually, we use some automated tools, but these tools each one of the tools could have their own limitations. For example, coming back to the Boeing's case, so it is actually very hard to find the bug with testing, because in order to test these type of, it's considered cyber-physical systems. It's like how we test those autonomous vehicles. So normally people will need to set up a simulation environment if we don't want to really test those features on a real plane. So we have to set up those simulation systems. And those simulation systems are not easy to set up. So there are limitations for these type of tools. For example, in this case, we can't simply use the Microsoft Flight Simulator to test and debug this Boeing's case, right? It is not possible to simulate everything. So there are unavoidable limitations for doing testing and validation. And the last one is about human factors. Because although we have tools, it is eventually the humans using those tools. And different people could have different levels of expertise and experience. So this may also cause some troubles. And you may understand this better when you do assignment 2, when you are actually using these tools. And that's all about verification and validation. And now let's come to the second topic today, different types of verification and validation techniques. So This is taxonomy for different techniques. So basically, we can see them as static methods or dynamic methods. And for the dynamic methods, we have many different basic types of testing techniques according to how much internal mechanisms of the target do we require for conducting the test. So if we know nothing about what's happening inside the target system, that is called a black box testing or functional testing, and we will cover that topic in week 2. And if we know every system state of the target system we are testing, it is called a white box testing, and we will cover that topic in week 3. And in between black and white, just like the real world, nothing's truly black and white except pandas. And so there are gray. So for testing is the same. We have gray box testing. So we just acquire the information that is needed for conducting testing. So we collect information from the system internals, but we don't collect every state of the system. So that is called gray box testing, and we will use it for our assignment too. As for the static methods, it is kind of out of scope for this course, so we won't cover any one of them. So, but we will roughly go through the basic concepts of these static methods. So the static analysis is related to analyzing the static artifacts from the system to discover problems. And remember, in our last lecture, we mentioned this example here. So consider the software as a patient and consider the detection tool as the doctor. So how can we detect the disease or bug? We can scan through the patient. We can scan through the software to look for patterns. And these patterns are called system artifacts, static system artifacts. And in the context of programming or in the context of software, this is an example. It actually looks a little bit blurred, but it is mainly about buffer overflows. So different situations of buffer overflows. In the first one is very straightforward. We have assigned buffer on an array with length of 10 bytes, and we are actually trying to access the 11th byte, and that will give us an overflow. And in the second one is a little bit more complex. We put the array access into a for loop, and we need to evaluate how many iterations the loop will go through to check whether a buffer overflow will happen or not. And in the third case, it's even more complex. But please. Yes. If there's a proper check here, if you avoid this overflow, yes. So as you can see, there are some basic patterns for us to check in the software. So given a piece of source code, we can look for these patterns to see if there's a potential buffer overflow or not. So that's why we can use static scanning of code to look for potential issues or bugs. So that's normally how static analysis works. But there are many different types of static analysis techniques. So for example, the first one is called formal verification. It is taught in COMP3142, and it is often related to you will need a very high level of expertise to do formal verification, and you may need some mathematical backgrounds to do it. So it's kind of to prove that So most of the time, for formal verification is to use some verification engine to help you to prove that the program satisfies certain properties. So for example, for a loop, you can verify that this loop will terminate. And for a variable, let's say for this variable I, index I here, you can verify that it is, you can try to somehow prove that this value will never go beyond the 10, let's say, then it is safe. So that's why formal verification can help us to check the dependability of software. And another typical static analysis method for detecting bugs is called software composition analysis. And software composition analysis, as described by the name here, is to analyze the composition of a given piece of software. It is used to analyze what are the packages and libraries used in this software. And you may wonder, why does this have to do with bug detection or vulnerability detection? This is because some of the libraries or packages could have bugs. And if we can identify a buggy version of library or package that is used in your software, then maybe your software is also buggy or vulnerable. So that's why software composition analysis could be used for detecting bugs. And the third one is called static tent analysis. And tent analysis is used to, okay, bye-bye. And static tent analysis is used to track the flow of values between variables and functions. So it could also be used to find bugs, especially those information leaking related bugs. And there are many more different types of static analysis techniques. And for dynamic analysis techniques, the key is that we need to exercise, or we need to execute the target system and observe the behavior of these systems and check if they meet the requirement or not. And remember the case of the patient and doctor. So the doctor can ask the patient to do something, so observe the behavior of the patient and check if there's anything wrong. And for software, we can do similar things. We can try to ask this software to do something, to run it with a particular user input, and see what happens. So if the software crashes or if the software runs into some errors, then it means that there's a bug behind. So that's why we can use dynamic methods to find bugs. And here is a quick summary of the advantages of dynamic analysis over static ones. So static methods are not good at discovering certain problems simply because of the nature that it is static. Because we are not running the program, we can never know certain runtime properties, like the execution time of the software, like the performance of different software components. So we can never acquire those or discover those issues with static methods. And for dynamic methods, another advantage is that it could be cheaper most of the time. So it is more scalable and more easier to automate. So for example, if we want to do formal verification, you need to write some formal specifications. You need to use the verification engine. You need a human to sit together with the verification engine to manage everything. So it is hard to automate. But for dynamic analysis, we can just build up test cases and feed the test cases to the system and run it and observe for what happened is relatively straightforward and easier to automate. So that's the second advantage. However, compared with static methods, dynamic methods does have its own disadvantage. And this disadvantage is that we cannot try out all the user inputs, because for most of the programs, the input space is like infinite. You can't define what the user will do, just like you can't expect what a student will do in a class. They may sit here or they may leave the classroom, so you can't expect. So the behavior or the input is infinite. So that's why dynamic, that's the limitation of dynamic methods. So it cannot exhaust all the possible states. So let's do a quick live poll and see if you could understand the differences between formal verification and testing. You can select multiple options actually for this question, so you don't have to select exactly one of them. Actually, all the software systems in the options are formally verified in real world. So for some, but not all compilers, but some compilers are formally verified, and some operating system kernels are verified, especially for those operating systems used in some critical scenarios, like those used in the airplane. So they are formally verified by human experts. And an emerging area in this formal verification is that nowadays we have a lot of smart contracts running on blockchains, and these smart contracts the code base are relatively small, and they are related to a big amount of money, so they are kind of considered critical, and they are formally verified. And actually there's a startup called Certic. It is funded by some verification professors in the US, and it is now the dominating player in this market. And it has reached 2 billion in 2022, and it's much bigger today. So we can see that form verification is still quite practical, although it is manually intensive. But you may wonder, okay, this is a testing course, why we are talking about formal verifications, why do we care about what systems could be formally verified? Because apart from all the systems listed in the options, all the rest of the software you are using today are tested. So almost everything here, other than these critical systems, are tested before they are released. So you can see that formal verification is more useful for those critical systems, while testing is more useful in daily scenario, because it is easy to automate, and it is much more scalable. And as you could see, there are so many verification and validation techniques. So how do we evaluate these techniques? There's actually no perfect technique, so it is actually a game of trade-offs. So software is the process of designing, constructing, and maintaining the best software possible given the available resources. So we do have resource constraints, we do have manpower constraints, we do have time constraints most of the time. So we are always trading off what we want, what we actually need, and what we get in the end. So it is either we could either make things better, faster, or cheaper, but we can only choose two of them. And most of the time, guess which one is satisfied here among these three desired properties. Which one is sacrificed? Better, faster, and cheaper. Which one? The last two? Actually, is better that is often satisfied. So normally we do have time constraints and we do have budget constraints, but we don't have a clear definition of what is better in most cases, and there's no perfect software. So in most of the cases, better is sacrificed, and we must accept that we must accept some degree of inaccuracy for software or program analysis. And talking about this inaccuracy, there are actually three types of inaccuracies. So the first one is called pessimistic inaccuracy. So it is pessimistic, so it is very strict. So it is not guaranteed to accept a program, even if the program possesses some desired properties. And this will give us some false positives, which means that this piece of code doesn't have a bug, but the technique will say that, okay, there's a bug because it is too strict. It is pessimistic. And the second type of inaccuracy is called optimistic inaccuracy. And this is to say that the technique may accept a program that does not possess a desired property. And because it is optimistic, it could have false negatives, which means that a buggy piece of code could pass through this checker, this type of verification and validation technique. And the third type of inaccuracy comes from property complexity, because this is also related to the scalability of the form verification. So because some of the desired properties are too complex to be modeled properly, to be converted into specifications, it is impossible to convert every real-world scenario into something that is verifiable. So we have to sacrifice certain properties. We have to simplify the properties. And in this simplification process, it may incur some inaccuracy. And as you can see in this, figure here, on the top is a perfect verification case where every user requirement could be converted into a specification and it could be properly verified. But that's the ideal case, and that is never achievable. And in most of the times, with formal verification techniques, we ended up in simplified properties, and we may have some inaccuracies because of this. And for the static methods, for example, static data flow analysis, it often runs into this pessimistic inaccuracy, which means that these methods are likely to give us some false positives. And for testing on the right-hand side, it could suffer from optimistic inaccuracy, which means that we may have false negatives. So there are bugs we couldn't find with testing. And talking about evaluation, we have two more properties to check for these techniques. So the first one is called soundness, and the second one is called completeness. So a technique is considered sound if it only reports true positives. So it never, if this technique tells you that, okay, there's a bug in the program, there's a bug in the software, then there is a bug. So there's never a false alarm. And this is called sound. And for completeness, it means that this technique could report all the potential bugs, all the issues, but it may give you some false alarms, and that is called complete. So do you think testing is sound or complete or both? It has optimistic inaccuracies. Excuse me? It's sound, yes. It is actually sound, but not complete. Actually, we have already mentioned this in multiple slides before. So we cannot exhaustively try out all the user inputs because the input space is infinite. So we can never be complete with testing, especially for those complex software. For simple software, maybe just a hello world, then we could completely test that simple software. But for most of the software we are using today, we cannot completely test them. So testing is not complete. But testing is often considered as sound because it is dynamic in nature. We are running the software. And if we observe that this software has some problem when it's running, then there must be something wrong, right? So it never tells a false alarm in this case. So that's why testing is often considered sound. So it is sound, but not complete. Most of the cases, in most of the time. So that's all about our second topic today, and let's have a 10 minutes break.
Verification errors is like errors in logic and like the purpose of like the program by humans. And then validation is like the errors in the code and that is like bugs. Is that it right?
Actually, for verification, the error mostly comes from the code.
The code, okay.
The implementation. And if we found some error in validation, there could be errors in the code or the specification given to the developer. The code. So that's the difference.
Because from what the slides say, that verification seems to be more like human kind of errors, like from just checking and stuff like that, and you need to use that to find errors in it for validation. You can like run the code to like check it. Is that wrong? So you have to get like a human to like read through it.
Ideally, there's something but sometimes you can look for patterns with some automated scripts. So that's the difference here.
Sure.
I missed yesterday's lecture, but I was wondering what the discussion about the Gangnam style bug was, with like the like counter.
Yeah, the correct answer is
Not correct, let's say.
It's kind of a line bug, but it has nothing to do
Yeah.
with some severe consequences.
Yeah.
start our second half, could you do me a favor to help me to test Echo 360 and see if the live streaming is working or not? Because it is supposed to be working. Okay, let's see the live stream. Alright, it might be validation issue, not verification. And as I told the teaching staff team to open live stream to this course, they told me that it's working, it should be working, but it's not working. So it could be a validation problem. It's not the fault of the.
Is the model?
Yeah.
The mic is
Oh, the mic is off. So, okay, the mic is on now, and we can start our second half. So, we have learned about the difference between verification and validation, and we have learned several different types of verification and validation techniques. And now let's see how could we use these techniques in real software development. But this is quite some kind of theory crafting, so you may not actually use it in real life, because for those big companies, they have their own standards and workflow, like they have to use Jira, they have to use GitHub Actions, they have to use whatever standard they have. And for small companies, normally they don't do testing, they don't do verification. They may, if they are developing some critical software, for example, smart contracts, they may outsource the testing to a third-party company like Certic. And if they are not creating these critical software, they may not test their software at all, because it is quite costly to maintain an internal testing team. So this is some borrowing definitions. So the development of dependable software needs a comprehensive plan for verification and validation. And actually there are 7 steps for us to do this kind of verification and validation planning. And the first step is we need to identify the verification and validation goals. So this actually must be identified early, and it should start from the requirements and specifications. So this is actually done for verification. And we should also consider, when we design the goals, we should also consider the actual user expectations. And this is for validation. So like for the example of the Boeing's case, so it is the software was conformed to the specifications, but it doesn't expect some real world corner case scenarios. So that's why it is not validated. And the design of the goals must be achievable. So we can't say that we want to build, our goal is to build a system or software that is free from any kind of bug. And that is almost impossible. So the goal must be achievable considering the time, the manpower, the budget we have. So that is step 1. And for step 2 is selection of verification and validation techniques. So we have different types of verification and validation techniques, and in different stages of software development lifecycle, we need different techniques. And there are some techniques during the requirement phase. There are some techniques during the specification generation phase, and there are some techniques to be used during the design phase. And what we are mostly interested in are the techniques used for implementation phase and maintenance phase in this course. So because we are more interested in testing, and testing is mostly used in implementation and maintenance. And for step 3 is to consider the organizational responsibilities. So there are different organizations or different teams related in this process of verification and validation. So the first organization, or it is so-called organization, but it's actually, you can consider it as a team. So the development team, or the software developers. So they are actually responsible to check the code works at a module level. So for example, the developers should write unit tests for their code. But normally they don't do that in real life, I know, but it is the responsibility of developers. And the second organization, or the second team here, is called the independent test organization. This is like the testing team in those big IT companies. So in many companies, they have, apart from the development team, they have an internal testing team to test the programs they have developed internally. So this team is often in charge of testing the developed software at a system level. So it's not like those unit tests. It's like combining everything together and see if the software works as a whole piece. So this is the responsibilities. These are the responsibilities of the internal testing team. And the third one is software quality assurance organization, or the quality assurance team. So you may wonder, okay, what's the difference between the quality assurance team and the testing team? This sounds like redundant, right? But actually, this is often the last step before a software is released. Especially in big companies, they have a lot of red tapes, but those are useful red tapes. And they have most of them, they have a quality assurance team that is in charge of checking both the quality of the software and the quality of the tests. Because the testing team, sometimes they may not develop a very valid test suite, or they may not test the software thoroughly, or they don't put enough effort to test the software. And in this situation, or in this scenario, the software quality assurance team, you come in and tell the testing team that you haven't done enough tests to make sure the software meets some standards. So that's why they need an independent team to check both the quality of the software and the quality of the tests. So that's the responsibility of the software quality assurance team. And the last one is independent V&V contractors. So like I mentioned, for some small companies, they don't have enough time and money to maintain an internal testing team, so they may outsource the testing tasks to third-party testers. Some of them may release bug bounties, and there are many bug bounty websites available online, and one of the most famous one is called HackerOne. And yeah, they are like hiring some individuals to do the testings for them. And of course, there are some professional companies helping other software companies to do the testing. So these are the 4 different parties or the 4 different organizations in this process. Okay.
You mentioned the first organization, the software dev team. They're responsible for correctness at the module level.
Yes.
And you mentioned the testing team is responsible for the correctness at system level. So what's the difference?
The difference is that I will explain the conceptual difference, but you may encounter, but there might be there might be no difference in real world cases. But ideally or conceptually, the developers are in charge of developing unit tests, and unit tests are more often developed or designed for small software components like functions or classes for most of the cases. And they may not care, but as a developer, as a responsible developer, you may want to make sure that your software works as a whole. But from the responsibility point of view, it's not the developer's responsibility to make sure that, okay, because let's use another example here. So, have you taken the course called, you must have taken the course 1531, right? You have developed a web page, the web development course. And in that course, you are doing some full stack development, right? But in big companies, there's a front-end team and there's a back-end team. And the front-end team is only cares about the correctness of the front-end, and the back-end team only cares about the correctness of the back-end. But who cares about the correctness of the system as a whole? And that is the testing team. So you can consider the situation like this. So, okay. So let's continue to the first step. So step 4, integrating V&V approaches. So this is another boring step. So once we have identified the goals or the objectives of verification and validation, and once we have selected the correct techniques to use, and once we have clarified the responsibilities of different parties, we need to combine them together. We need to somehow construct a more concrete plan, combining those goals, techniques, and responsibilities. And this is called integrating. And this integration often depends on the development methodology. So if you are doing a waterfall approach, you may do it, you may have a plan first and then you do everything else. And if you are doing agile development, you may have different sprints. So you are doing it in a recursive way. So that's how we do this integration. And for step 5, we need to do problem tracking. So, because for verification and validation, ideally there's no bug detected, nothing went wrong. But in reality, the meaning of having a testing team is to find bugs. And once we have found a bug, we need to somehow track the problem. And this problem tracking involves documenting the problems and routing the problems to the correct party to fix them. Because our ultimate goal is not just to expose bugs. As a software development team, we should eventually fix the bugs. And after fixing the bug, we should somehow ensure that this correction is done and it is made correctly. And typical information to be collected for tracking these problems are when the problem occurred, because some problems or some bugs are time sensitive. And maybe you don't know about this case, but there's a famous bug during in the year 2000, because we are going from one century to another, and the timing system of some operating system went wrong, and that caused some bugs. But that's a very old bug. And so some of the bugs are time sensitive, so we need to track when the problem occurs. And of course, we are interested in where the problem occurred, because we need to locate the bug or vulnerability. And we need to know the state of the system before occurrence. So this is helpful for us, for the developers to debug. And we also need the evidence of the problem. So we need to somehow show that there is such a problem. And the last one is the priority for fixing these problems, because in reality, when you develop a software, there could be a lot of bugs or a lot of issues, and you should prioritize the most important ones. And talking about the information to be collected, an advantage of testing is that we can use test cases naturally as the evidence. So, do you still remember what is a test case? A test case is like a user input we use to run the system. So we can naturally, if we find a bug with a particular test case, we can naturally use that test case as an evidence for the existence of the bug. And we can use it, we can give it to the developer to do debugging. And this is the advantage of testing.
Are test cases like developed when you're doing like test-driven development, like along with like a class? So like if you develop a class for like, I don't know, say it's an XYZ class, and you'll have like a test case for XYZ.
Oh, that's that test case is more like it's more like a test harness, harnessing so for different scenarios, test case the definition of test case could be different. So if we do a system level of testing, the test case could be the test case could be the input of the system. And if in the case you mentioned during the test-driven development, you are writing some small pieces of code invoking the target function or the target module you want to test, but you are feeding the target function or the target class or whatever with some particular input, right? The function input. And we call those input test cases, but we don't call the small program test case. The small program, more accurately, it is considered as a test harness. It is used to harness the tested target. So that's the more detailed definition here. So, okay. And why this is an advantage of testing is it is because if we do static analysis, like we have found a pattern of the program that could be buggy, and if we use this as an evidence to show it to the developer, most of the time it will cause some kind of confusion. And they just say, okay, my code matches this pattern, but I don't know exactly why my code went wrong, right? And for example, if we do software composition analysis, it will report us, okay, you have, maybe if you are using GitHub, you may receive emails from GitHub saying that you are using a vulnerable version of library. Sometimes if your repository are actually using one of them. So this is actually done by the software composition analysis of GitHub. And this is often confusing because you don't know, just because I'm using a vulnerable version of library, it doesn't mean my code is vulnerable, right? Maybe I didn't use the vulnerable function inside that library. Maybe I just used that library. So that's the drawbacks of the other techniques. And let's continue to step 6. So step 6 is related to tracking testing activities. So the software validation and verification and validation plan must have some kind of mechanism to track the testing process, because most of the time it's not only enough to just ensure to just debug or to just identify bugs from the software. We have to somehow show our customers or show someone else that we have done testing. And you may think that this is pointless, but actually in reality it is very important, because this is especially important for certain type of software. For example, for the autonomous driving systems, it has to acquire some kind of certificate saying that, okay, this system has been tested under whatever circumstances, under whatever simulations, in order to meet the standard given by the government. And different governments could have different standards. So we have to have some kind of mechanism to collect or to track the testing activities and demonstrate this testing effort to the parties who are interested in our product. So this is important. And normally here are the information that is collected for this purpose. So we collect the number of tests executed, the number of tests remaining, time used, resources used, number of problems found. And the last step for this software verification and validation plan is assessment. So this is somehow related to tracking the testing activities. So it is important for the plan to provide the ability to collect data that can be used to assess both the product and the testing results or the testing report. And remember, when we were discussing the different parties or different organizations, we do have internal testing team, and we do have an internal software quality assurance team. And the responsibility difference between these two teams are, the testing team only cares about testing, but the quality assurance team cares about both the quality of the software itself and the quality of the tests. So we have to somehow have some mechanism to assess the quality of the tests. And this is our last step. So these are the 7 steps for software validation and verification planning. So the first one is we need to identify the goals. We need to select proper techniques, and different software development lifecycle stages may have different techniques. And we are only interested in implementation and maintenance related techniques. And we have organizational responsibilities. We have integrating approaches, problem tracking, And we know that testing is good at providing evidence for problems. And we also have tracking test activities and assessment. Okay, that's all about the third topic today. And let's come to the last one, the principles of analysis and testing. So there are 6 basic principles for testing. So the first one is called sensitivity. The second one is redundancy. The third one is restriction. The fourth one is partition. Fifth one is visibility and observability. And the last one is called feedback. So let's talk about the first principle, sensitivity. So faults may lead to failures, but faulty software may not always fail. Let's take the buffer overflow in C programs as example. So if we read a buffer with one more byte, does the program crash? So have you taken the C programming course? You must have taken the data structure course, right? You are using C in that course. So if your program reads a buffer with one more byte, does it crash? Normally it doesn't. In most of the cases, it doesn't crash. So if you just read one more byte through a pointer of a buffer, it doesn't crash. But what if we are writing 10 more bytes to a particular buffer? Will the program crash? Normally it will crash. And if you know some basics about writing exploits for C programs, you know that this writing right out of bound is often exploitable, and you can write some design payload to hijack the program execution and inject some logic into the program. So in this example, we could see that some errors may not lead to observable failures. So the program will just silently go wrong. So it doesn't report failures. So we cannot observe for failures during testing. And the sensitivity problem is that it is always better to fail every time rather than only during some executions. So if an error occurs, it's better to fail the program and make it observable rather than just letting the program continue to run. So this is called sensitivity. And this is related to trying to make the faults easier to detect by making them causing failures more often. And to deal with the problem here, we could use some sanitizers during the compilation of these C programs. And one of them that is dealing with these memory errors is called address sanitizer, and it is maintained by Google. And you may need to use this one during assignment 2. And but you just need to use it. You don't need to know why it works and how it works. And another example is for this kind of sensitivity issue is sometimes the programs may not just crash. It may have some logic errors that doesn't crash the program. Remember the Gangnam Style example in our first lecture. So the YouTube website doesn't crash, but it runs into some problem that is observable by human but may not be observable by programs. And that kind of, how do we deal with that kind of failures? If we want to catch those logic errors, normally we will need to design some kind of assertions to just let the program crash so that it is observable by the testing tools. So this is about the sensitivity principle. And let's come to the second principle, redundancy. Redundancy is related to having multiple tests or mechanisms to check the same functionality. So this increases the likelihood of catching errors because we know that testing is sound but not complete. And different testing techniques could have their own advantages and disadvantages. And since it is not complete, why don't we just somehow try to combine some complementary techniques and let them work together to test our system so that we could improve our coverage, so that we could somehow increase our confidence that this software is free from bugs. So this is the key idea behind the redundancy principle. It is just to have some alternative ways of testing the same software. And one of the examples is called ensemble fuzzing, and you will encounter this concept in assignment 2 as well. So this this ensemble fuzzing is actually this is a link. Like the address synthesizer, if you have a laptop with you, you can click through the link and check out the related resources. And the idea of ensemble fuzzing, in short, is just to orchestrate multiple fuzzing techniques to make them work together, so that they could complement each other and try to expose the errors that a single technique couldn't. And the third principle here is called restriction. So sometimes the properties of the programs are very hard to check or validate. This is especially obvious when we are doing formal verification. We cannot convert all the real-world user requirements or the real-world usage scenarios into something that is that could be formally specified or that could be tested. So we have to add some limitations. We have to add some restrictions so that we can work in a smaller domain or a smaller set of programs. So here is another example. So in this example here, we have defined, declared a variable k, and we will use it in this branch if the condition for I is not satisfied. We will use it here. Otherwise, we will initialize the value for k. And this program could have a problem that if this condition isn't met, and we could add I to an uninitialized k. But actually it is very hard. So this program has this problem. So k can be uninitialized the first time when we reach this line of code. And this is very hard to determine because the condition here could be very complex, and it's hard to determine this. And what most compiler would do is to just don't allow this program to compile because there's one execution path that it goes through the initialization and then goes through the adding of I in the next iteration. That is correct, but it could go through this path. And so the solution here is to add some restrictions. So we don't allow the compilation of once if there's a potentially uninitialized variable. So this is kind of restricting the set of programs we are dealing with. So this is the principle of restriction. And we also have the fourth principle here, which is called partition. So the idea of partition is divide and conquer. And the best way to solve a problem is to partition it into some smaller ones that are more doable. So in the scenario or in the context of testing, we could divide testing into different levels. We could do unit level testing, we could do system level of testing. And levels of testings will be discussed in week 4. So we will discuss different levels of testings in week 4. And this is called partition. And the fifth principle here is visibility and observability. So visibility is the ability to measure the progress or status against goals. So we need to measure the progress of our testing. So this is important. And we also need to measure the status against what do we want to check, what do we want to test. And observability is the ability to extract useful information during testing. So for black box testing, we don't have any knowledge about what's happening inside the target, but it is still observable because we can observe the overall output of the black box of the system on the test. And for white box, it is more obvious. We can observe the system states of the white box of the system we test. And that is called white box testing. And for gray box, we can use some kind of techniques called program instrumentation to collect whatever information that is useful for testing during the process. And that is called gray box testing. And that is what we can observe from these testing techniques. So observability is important. And the last one is called feedback. So the feedback principle is that we should be able to apply lessons from experience in progress and techniques. So in static analysis, or like the systematic inspection and code walkthroughs, those are the manual process. And this principle is quite obvious, right? Because they are done manually, so we can easily apply the experience, the human-based experience during that process. And in testing, because most of the testing techniques are automated, so what we can do is we can prioritize our test efforts, because we do have limited resources and we have limited time. That's one concern. We have limited computational resources, because in order to scale up our testing process, normally what we do is we can run multiple testing processes in parallel, maybe on a server or on a big machine. And that, in that case, we are limited by the computational resources. So we should, but we don't have infinite time. We don't have infinite machines for us to do testing. So we have to prioritize our testing efforts to focus on the targets which are more likely to be faulty. And this is somehow related to software complexity, and that is to be covered in week 7. So you may wonder in our last lecture, why are we learning software complexity in this software testing course? That is because it is not proved, but it is said that complex software, or it is commonly accepted that complex software are more likely to be buggy. So we want to analyze the complexity of different code. So that's why it is related to this course, and it will be covered in week 7. And in this case, we are in sometime we analyze the software complexity before we do testing, and we focus on testing the more complex part of the code. So that's the idea of feedback, and that's pretty much of all the content today. And before I let you leave, let's quickly go through what we have learned today. So in the start, we learned about verification and validation. So can you think about what's the difference between verification and validation? So do you still remember the difference? I hope you can remember the difference. And the difference is, for verification, we are trying to build the product right. So it is more about how we build the product and whether it is aligned with the specifications or not. For validation, we are trying to see if the software meets the actual requirement of the users. And in this case, the specifications could went wrong, and it could be captured by validation. So that's the difference between validation and verification. And we also talked about different limitations of verification and validation. So there are limitations regarding to the complexity, the complex nature of these processes and the target software. There are restrictions about the incomplete coverage, and that is some kind of theoretical limitations. And there are limitations with regard of the tools we use, and there are limitations with human factors, the ones who are using the tools. So these are the limitations of verification and validation. And after that, we learned different types of verification and validation techniques. And in this course, we define testing as one of the validation techniques, and it is a dynamic process. And we also learn about different metrics for evaluating these verification and validation techniques. We learn about different types of inaccuracies: pessimistic inaccuracy, the optimistic inaccuracy, and the simplified properties. And testing suffers from the problem of optimistic inaccuracy, and testing is sound but not complete. And that's what we learned about the second topic today. And the third topic we learned today is about the software verification and validation plan. It is like how we apply it and how it works in real software development life cycles. And we know that we need to set up a goal first. That is our first step. And our second step is that we should select the proper techniques to use. And our third step is that we should identify or clarify the responsibilities of different parties. And we learned about the differences between different parties. And different organizations, of course, they would have different teams, but normally they should have those parties in their organizations. And please.
What's an example of a V&V goal?
An example of V&V goal. Okay, that's a good question. So, for example, it must be measurable and it must be achievable. That's the most important thing. So, for example, we can say that we have, let's say we have developed maybe the V&V goal could be we develop 100 test cases that could cover maybe 90% lines of code. And this is a valid V&V goal. So it is measurable. And that's the goal here. So, and it should be achievable. We can't. Normally you can't say we achieve 100% of code coverage or line coverage. That's not possible in most of the cases. Yeah, and sometimes another example of V&V Go is because the purpose of testing is not just to ensure the quality of the software in real life. It is also to show a proof that the quality of the software has achieved certain level and could meet certain standards. And those standards could come from the international standards, could come from different governments, different policy makers. So those policies or those standards could also be adopted as V&V goal. So we can say that, okay, our goal is to meet certain standard, and that is also a valid goal here. And after that, we covered some other steps. We covered some other steps in software V&V planning, and another important fact here is that testing compared with static analysis is good at providing evidence to show the bug, to show the existence of the bug, or to help the developer to debug. And that's our third topic. And our last topic are the 6 different principles of testing. And you may encounter the concept of these principles later when you continue the study of this course. And that's all the content today. And thank you for coming.
Week 3? What, so we only have 1 week to do it?
Yes, it's not very.
Is it
you keep you busy for 1 week. So
is it practical?
Not very. It's more about checking your understanding about the series of week 2 and 3.
Oh, I thought we would be able to. It would give us like code, and we'll have to write like tests for it using the knowledge that we got. That'd be pretty cool.
Yes.
Is that how it is?
Yes.
Oh, easy.
You may also encounter some MCQ.
Pardon?
You may also have some MCQs.
MCQs, yeah.
So it's more about testing your understanding of the series.
I was wondering, for the lectures, would it be possible to have like some code, like examples of like the stuff that you're like talking about, like because that would make it a lot more
Yeah,
clearer?
in the next week I will have some code examples because when we are dealing with some specific techniques
Yeah.
talk about code like multivariate testing or the decision tables.
Because like usually like a little bit of just like a terminal open, like just look at the terminal.
Yeah, because here in
Yeah.
design it's more like some
Theory stuff.
Yeah, there's
Yeah, just set the foundation. Yeah, easy. That's good.
I'm curious, because I wasn't here during the last lecture. Did you mention like which languages specifically? Like we'd be doing assignment 2 in?
Oh, one. This assignment 1 is also in code. Yeah.
For assignment 1, you may I'm planning to use C proposal.
C.
Yeah. For assignment 2, you can use whatever you like. But the target we are testing mostly C and C++.
C++ is good. Yeah. I'm employing C++.
But you can use whatever language you like.
Yeah. So with the team, because I heard that like the second assignment is a team project, right? So does that mean that like we get assigned like a language because everyone needs to, or does it just the team like just use the same language?
I will make some announcement later. So it's better that you form your own teams first, and then if you cannot form a team, find a team until week 6, we will find a team.
Because it's a bit harder, but usually like the teams are formed like inside the tutorial, and
yes,
because like there's no
have
tutorial,
yeah, this class we don't have a tutorial. This is the first time.
If you don't mind, can we?
Sure.
Yeah.
Because we started to. We can continue speaking. Just to figure out how it works. Some exciting time in the coming 10 weeks.
Thank you.